In our previous lecture, we explored the limit definition of the derivative. Next, we're going to use the limit of that definition of the derivative to compute the derivative of a few actual functions. So we'll see a few examples of how that limit definition is actually employed to compute the derivative. Later on, we'll explore various techniques where we can go directly to the derivative just by using simple rules. But where do those rules come from? They always come from this limit definition. So any of the rules you use to do a quick technique where you can get a derivative in a flash always stem from this limit definition. So it's very important to understand this limit definition and how it works so that we know what the rules are, and we'll learn how to compute these derivatives very quickly. So just a reminder, the definition is f prime of x is equal to the limit, h goes to 0, f of x plus h minus f of x over h. Okay, so our first example, so compute the derivative of f of x is equal to 3x plus 7. So first of all, I'm going to tell you that the answer is 3. So first, we'll say our guess is f prime of x is equal to 3. Now, I didn't use any magic to figure this out, and I didn't use any knowledge beyond what you have right now. I figured this out because the function that we're looking at is a line. So this function that we have, so here's maybe 7. So this is f of x is equal to 3x plus 7. So the vertical intercept is 7, and then the slope of this line is equal to 3. Now remember, the derivative returns the instantaneous rate of change, which is equal to the slope of the tangent line. Now when your original function is linear, so when its graph is a line already, its tangent line will just equal itself. So if I say, well, what's a tangent line at this point? Well, it's the line 3x plus 7. If I say, what's the tangent line at this point? Again, it's just the line y is equal to 3x plus 7. So the tangent line will always have a slope of 3, so therefore the derivative has to equal 3. In other words, linear functions are functions whose derivative is a constant, right? They're always changing at the same rate, right? If you're driving at a constant speed, let's say 50 miles per hour, and you plot your distance as a function of time, you'll have a nice linear function whose slope is 50 miles per hour. But we can still gain additional insight, even though we figured out this answer just by thinking about it, by going through and actually using the limit definition to compute it, because this is the easiest type of function you can use the limit definition on. So let's see how the limit definition works and see if it really does give us 3 for the derivative. So here's our work below this line. Okay, so we always start off by saying f prime of x is equal to, and then we're going to have a chain of events that are all equal to f prime of x. So first, let's just right out of the box, write out our limit definition. Limit h goes to 0, f of x plus h minus f of x divided by h. Okay, so now is equal to. So now we take the function f of x and we plug it into this equation. So there's a few things we'll need, and I guess this first time I'm going to have a few notes on the bottom. I don't normally these things I write in my head, but let me just write it out down here. So f of x plus h. We have to take x plus h and insert that into the function for x. So it's very important that you don't think of it like that. So that's a common mistake. And we'll write out what, because this one is just 3x plus 7 plus h. Right? So here's f of x, and then here's plus h. So this is not what we want. right? So this is not, we're not interested in this, right? No thanks. What we want is f of x plus h, where the x plus h is all inside the parentheses. So we have 3, we see an x, wherever we see an x, we replace that x with an x plus h. So 3 times x plus h, and then plus 7. So this is the one we want for f of x plus h, not this guy down here. I'll do an asterisk since x looks like x. So it's 3 times x plus h and then plus 7. And then, of course, we distribute the 3. So it would be 3x plus 3h plus 7. You can see how f of x plus h differs from f of x plus h. Okay, so that means that we get the limit as h goes to 0 of 3x plus h plus 7, and then minus 3x plus 7 all over h. So another thing is to note that whenever you're computing these derivatives using the limit definition, you always kind of do the limit last. So first step is to just take that difference quotient, this delta y over delta x, the f of x plus h minus f of x over h, plug the function into there, simplify things, and then once you have it simplified, then you take the limit as h goes to 0. So when we're writing this limit as h goes to 0, that just kind of gets carried along for the ride until we actually go out and take the limit. So right now we're just simplifying what we're taking the limit of without actually taking the limit. So the f of x plus h is this guy, and I put some square brackets around it, then minus f of x, which is minus this one. This is another common mistake, because note it's minus f of x. So you have to add some parentheses around f of x, because it's minus the whole f of x. So we're subtracting 3x, and we're also subtracting the 7. It's not minus 3x plus 7. This minus sign has to distribute into every term of f of x. If you don't distribute this minus sign, you're not going to get the right answer. A little tip so that you know that you're on the right direction. Usually the stuff in f of x cancels with something in f of x plus h. So we'll see what that looks like in a second. So this is equal to, again, limit just stays along for the ride. I'm not ignoring it. I'm not writing it because I've got an equal sign. So these all have to be equal expressions. These are all equal to f prime of x. All I'm doing is just taking what I'm taking the limit of and simplifying it. So here I'm going to do the distribution. So it's 3x plus 3h plus 7, and then minus 3x, and I'll distribute this minus sign too, and then minus 7 all over h. Now once you have the function f inserted for our general formula here, and you FOIL stuff and expand it out, this is where it gets fun, because it's like like a war game, like Risk, where you have all the soldiers lined up, and you roll the dice, and so many of them get wiped off the board, and so that's what happens here, because there's lots of simplification. And this is just a linear function. When you get to more powerful functions like x, quadratics, cubics, there's more terms that cancel out. So there's more going on. So it's a fun thing to play with your friends, see who can compute these the fastest. It's something to do on the weekends. Okay, so let's simplify. So the 3x minus 3x cancel out. Plus 7 minus 7 cancel out. So this is now equal to the limit as h goes to 0 of 3h over h. Now the function 3h over h is not equal to 3 because the function 3 is defined at 0, but 3h over h is not defined at 0. However, we're taking the limit as h goes to 0. So when we take the limit as h goes to 0, we actually, the only point we don't care about is the point h is equal to 0. Because remember, what's happening at that point when you take a limit does not matter. It's just what happens as you approach h is equal to 0. So for that reason, since we're not interested in the actual value h is equal to 0, we can actually simplify this and say it's equal to the limit as h goes to 0 of 3. Now this no longer depends on h. So when we take the limit as h goes to 0, nothing happens, so we just get 3. Perhaps if you want to be a little bit more careful, depending on your instructor, some instructors might be okay with the way I wrote this up. Some might not want to see you cancel the h over h. So if you think of just the function 3h over h, so there's 3, 2, 1. It's a function with a hole in it, right? So when you take the limit, oh, that's not x, that's h. So this is y is equal to 3h over h. So it's a straight horizontal line with a hole in it. So when you take the limit as h goes to 0, you just get 3. So either way, the answer is 3. I never broke the equal sign, so f prime of x is equal to 3, just as I predicted. Okay, so the next one, so this is going to get even more fun, is f of x is equal to 3x squared plus 4x plus 7. And again, we want to compute f prime of x using the limit definition of the derivative. Now, we don't have that handy-dandy thing that it's a linear function anymore, right? Who knows what the derivative is? It's some function of x. Right? It's not a linear function, so there's no way without using the limit definition at this point to figure out what the derivative function is. Unless you want to actually compute the instantaneous rate of change separately at every single point you might be interested in. But the power of the derivative is once you have the derivative, in order to compute the instantaneous rate of change at any point, you just take the derivative and evaluate it at that point. So let's see what we get. So again, we start off by writing f prime of x is equal to, so we start off with just the limit definition. Limit as h goes to 0, f of x plus h minus f of x over h, and always have that picture in your mind, delta y over delta x. So we have the interval from x to x plus h. F of x plus h is the right endpoint, f of x is the left endpoint. So if you keep that picture that I showed you in your mind, you'll never have to memorize this because this formula makes sense. All the formulas make sense. Since they make sense, there's little memorizing. If you see it and understand why they work, you'll remember what they are. This is basically delta y over delta x, and then you take the limit as h goes to 0. Okay, so now let's plug in the function. So it's 3, and then we have x plus h squared plus 4 times x plus h plus 7, and then minus f of x. So 3x squared plus 4x plus 7. So and then all divided by h. And this is not an inequality because this depends on x, or it depends on h, where this guy doesn't. I forgot to write the limit. So let me get rid of that equal sign, move a little bit to the left, and say the limit as h goes to 0. Right? Because these two things have to be equal. If you link up two expressions with an equal sign, they should be equal to each other. So I don't want to leave off the limit. So we wrote it like that. So now we want to expand this out. So we have to square this guy. So x plus h, well, first of all, just to make sure you see where I got this, I plugged in x plus h for x. So when I have an x squared, it becomes x plus h squared. When I have x, it becomes x plus h. And of course, the 4 now has to distribute. And notice again, the minus sign and everything here is in parentheses, so that minus sign will distribute to all of those terms when I subtract off f of x. So it's equal to the limit as h goes to 0. So now we have, so x plus h squared is x squared plus 2xh plus h squared. So you can FOIL that out if you want, if you don't know it. And then we multiply that all by 3, so we get 3x squared plus 6xh plus 3h squared. Onto the next term, distribute 4x plus 4h plus 7 minus 3x squared minus goes in, minus 4x, minus distributes in, minus 7, all divided by h. Okay, so now the fun part comes. We get to see what cancels out. All right, 3x squared minus 3x squared. Off to a Good start. 4x minus 4x. Pow, pow. 7 minus 7. Just like that. So that's equal to the limit. H goes to 0. 6xh plus 3h squared plus 4h all over h. And again, even the h over h does change it. We're not interested in h is equal to 0, so I'll cancel out the h over h. So this is also something, when you do a cancellation like this, I have an h on the bottom, and there's a factor of h for every term in the numerator. So you can only cancel this if h cancels out of every single term in the numerator. And the reason is because I really pulled out an h. It's really h times 6x plus 3h plus 4. And then that h can distribute back in, right? So really, you have to pull the h. There has to be an h in every term in order to pull that h out and then have that cancel with the denominator. So that's another common mistake. You see people canceling when you can't cancel, or only canceling one of the h's, but there has to come an h from every term. And the reason is because, a plus b plus c over d is equal to a over d plus b over d plus c over d. So if you're going to cancel the d out, a has to have a factor of d, b has to have a factor of d, and c has to have a factor of d. So it has to cancel from every single term in the numerator. So that said, the h down here cancels one h from each term, and so then we have the limit. So it's equal to the limit as h goes to 0 of 6x plus 3h plus 4. Now remember, x for our purposes now, before we take the limit, is a constant. So 6x is held fixed, 7 is held fixed, 3h varies. So basically this is the average rate of change between x and x plus h. It depends on where x is, and it depends on h. But as we let that average rate of change be over a smaller and smaller and smaller interval, so as h goes to 0, this is going to approach 6x plus 4. So this limit as h goes to 0 just gives us 6x plus 4. So therefore f prime of x is just equal to 6x plus 4. So that's our second example of taking a derivative using the actual limit definition.